Okay, changing to writing mode. Alright, cool, there we go. Oops, let's remove that. Make it a little smaller. There we go. Okay. So, last time we left off with taking the derivative of vector valued functions. Okay, so we're gonna continue again with that. So, we learned, as he talked about this, that like, look, when you're dealing with like a scalar function, so in other words, you input a scalar and then you output a scalar, that what does the derivative tell you? The derivative tells you the slope of the tangent line. So I have like a picture right here. You can see that you have your function f of x, and then you have that point at x equals a. If you calculate the derivative at a, you get the slope of that tangent line. So we were wondering, like, well, how does that work for vector valued functions? Well, it's basically the same thing, but you have to be a little careful about how this works. So I did an example with a plane curve. So you input a scalar and it outputs a vector in R2, right? So because it outputs a vector in R2, you have a x component and a y component, right? That's why you have r of t equals x of t comma y of t. Okay, and then the question becomes like, okay, so when you calculate this derivative, like, what does that mean? Oh. Okay. So you calculate these two vectors. You have r of t plus delta t, and you have r of t. So you can see in the drawing right here that I have my two vectors, right? I have my green vector and I have my blue vector. The green vector is r of t, right? That's your vector at some t value. Now r of t plus delta t, the blue vector, is some vector at some time t plus delta t later, right? So you have the green vector and you have the blue vector. And then you notice that in the difference quotient, you're taking the difference of those two vectors, which is why off on the right you can see we looked at like, well, if you have a vector A and you have a vector B, then what is B minus A? Well, it's a vector that goes from the terminal point of one vector to the terminal point of the other vector. So you look at this, you're like, okay, cool. So if I'm going to subtract those two vectors, I'm going to go from one terminal point to the other terminal point, which is why I have this white vector, right? And if you look at this, what does that look pretty close to? So tell me, if you look at it, what does that look pretty close to? That white vector looks a lot like what? Oh no, is anyone listening? I'm like the sad sheen. Okay, yeah, it looks like a secant, well, very close. It looks like a secant line, right? But it also looks like a tangent line. So the idea is that if you let delta t go to 0, t and t plus delta t will get closer and closer and closer and closer and closer, and eventually you'll get the tangent line, or the tangent vector is what we're going to call those. Okay, right? And so then I drew the picture right here. Right? You can see that you have your green vector r of t, and then you have your blue vector r prime of t, your derivative. The two of those form a right angle with each other. They're orthogonal, right? Okay, and then I did an example of this. So we had r of t equals 6t minus 8i plus 4t squared plus 2t minus 3. And we found out that if you go and you calculate the limit, it's pretty easy to do the derivative. You just take the derivative of the components. Alright, so like, what were we going to get for our x component? Well, what is the derivative of 6t minus 8? It would be 6. What is the derivative of 4t squared plus 2t minus 3? 8t plus 2, right? And you can see that we went and we calculated it, and that's exactly what we got. Okay, so hopefully that reminds you of what we did last time. Okay, so then what did we move on to? We started wondering like how the derivative of vector valued functions plays with the other vector operations that don't exist for like scalars. So like, you know, what happens if you mix the derivative with the cross product? What happens if you mix the derivative with the dot product? And how would you describe it? If you look at rules 4 and 5 here, if you mix the dot product and the cross product with the derivative, what does it look a lot like? What do you get? Or like, what should they like remind you of, these rules? Vera Majo. Tis me. Yes, the product rule. Okay, cool. Okay. So we have these rules that look a lot like the regular derivative rules. You have like the constant multiple rule, which we call the scalar rule. We have, the sum and difference rule, right? You can just add them like that. We have the scalar product rule. We have these product rules for the cross product and the dot product. And then you get another one actually. So there's a special version of the chain rule. So let's say that you want to take the derivative of some vector valued function r of f of t. So looking at these two functions, I have an r function and I have an f function. What is the difference between them? What sort of function is r and what sort of function is f? So like we have like the two possible functions. We have scalar valued and we have vector valued. So like f is a scalar valued function. So like you plug in a scalar and it spits out a scalar, and then that scalar is plugged into r, which spits out a vector. Okay? So it works basically like you would expect the chain rule to work. You're going to take the derivative of your vector valued function r and plug in f of t, and then you're going to multiply that by f prime of t. Okay, so remember f is a scalar valued function, f prime is a scalar valued function, and then r prime is a vector valued function. One second, I need to go turn off my what's it called? My tea. It's, what's it called? It's boiling. So just one moment. Alright, there we go, I'm back. Okay, so let's use these rules to do some like calculations. Moving my foot, sorry. Everything's like not adjusted on my desk properly. Alright, so let's do some examples using the rules. Okay, so let's say that you have some vector valued functions. One of them is r. So your vector valued function r is equal to 6t plus 8i plus 4t squared plus 2t minus 3j plus 5tk. So looking at this, you can see that it's a space curve. You could write it in component form like this. You could write 6t plus 8 comma 4t squared plus 2t minus 3 comma 5t. So hopefully you can see how the unit vector form and the component form, they work the same. Okay, there's just different ways of writing it. And this is a space curve because you can see that it inputs a scalar t and then outputs a vector in 3 dimensions because you have the 3 components. Okay, and then let's have another vector called u of t, another vector valued function, called u of t, which will be t squared minus 3i plus 2t plus 4j plus t cubed minus 3tk. Okay, so I've got my two vectors here. Okay, so let's calculate first the derivative with respect to t of r of t dotted with u of t. Okay, so there's several different ways that you could approach this. Okay, you could first dot everything in here. So you could do the dot product and then the derivative. Okay, or you can use the product rule. Okay, you would get the same answer. So let's use the product rule. So the product rule tells you, well, I need to take the derivative of r prime of t. I'm going to dot it with the vector u, or the function u, and then I'm going to add r dotted with the derivative of u. Sorry. So let's set this up and go through the calculations. I like doing this in component form, so we're going to do it in component form. So if you look at your component form of r, you take the components piecewise, remember? So the derivative of 6t minus 8 is going to be 6. The derivative of 4t squared plus 2t minus 3 is going to be 8t plus 2. And the derivative of 5t is going to be 5. Okay, so that's your r prime of t. Okay, then now you're going to have to dot this with u, which is going to be t squared minus 3 comma 2t plus 4 comma t cubed minus 3t. Okay, then you're going to have to add to it r of t, which is going to be in component form 6t plus 8 comma 4t squared plus 2t minus 3 comma 5t. And then now you're going to have to dot that with u prime. So if you take the derivative of the components of u, you're going to get 2t comma 2 comma 3t squared minus 3. Dang, that's long. So you keep trucking. We're at the dot all of this. Okay, so remember the way the dot product works is you multiply by components. So you're going to get 6 times t cubed minus 3 plus 8t times 2t plus 4 plus 5 times t cubed minus 3t plus, let's change color. Oh, actually, no, let's not change color. Just put brackets around it so you can see that this came from that one. And then when you do the other one, you're going to get 6t plus 8 times 2t plus 4t squared plus 2t minus 3 times 2 plus 5t times 3t squared minus 3. Oh my god, so there's just so much arithmetic you have to do. So, deep breath, let's do it. Multiply the 6, so you get 6t squared minus 18 plus 16t squared plus 32t plus 5t cubed minus 15t plus 12t squared plus 16t plus 8t squared plus 4t minus 6 plus 15t cubed minus 15t. Holy fuck. So long. Okay, now we start grouping terms. So let's look for all the t cubes. So you get a 5t cubed plus a 15t cubed, 20t cubed. And we move on to t squareds. So 6t squared, 16t squared, 12t squared, 8t squared. So if you add those together, 6 plus 16 is 22, 22 plus 5 is 27, 27 plus 5 is 32, 32 plus 10 is 42, 42t squared. Okay, now we have to look at all the t's. 32t minus 15t plus 16t plus 4t minus 15t. So if you look at the two minus 15t's, that's a minus 30. Okay, and then if you look at the two 16s, that's positive 32. So that's going to leave you with a positive 2, and then you have a plus 4 right here. So that's going to be a plus 6t. Okay, and then finally we're left with the constants, minus 18 and minus 6, which would be minus 24. Okay, so notice, this is a little interesting, we're taking the derivative of a dot product, and you get this function, which is a scalar. So notice you don't end up with a vector, right? Because when you dot something, you get a scalar. So if you're taking the derivative of a scalar, you get a scalar. Okay, so like whenever you finish these, you need to look to see if the answer you're getting makes sense. Like if you take the derivative of a vector valued function, you should get a vector valued function. If you take the derivative of a scalar valued function, you should get a scalar valued function. R dotted with u is a scalar valued function. You take the derivative of a scalar valued function and you get a scalar valued function. Okay, any questions about the steps so far? Yeah, this is the first thing I've done so far. Okay, so I'll keep going then. Let's do another example. So for this one, I want to do, oops, why is it not letting me write? Oops, lower. I want to do the derivative with respect to t of the vectored valued function u crossed with the vector valued function u prime. And before we calculate it, I sort of want to talk about why this is interesting. Okay, so let's draw this. Let's say that this is my vector valued function u.
Professor, can you go on real quick?
Yeah, sure. I guess I'll leave that there for a moment. So I'll just go and get my t right now while you copy that. Good reason to go get my tea. Okay, can I scroll down now?
Yeah, I'm done.
Okay, cool. So, this is actually a really common thing that we're going to come across. This is why I'm going to do an example of it, but I want to explain why we come across this very often. So you have u of t. That's your. So does everyone see? Hopefully you see the blue vector u of t, or yeah, u of t. Now u prime of t. How should you draw that in relation to this blue vector? So we talked about this last time. If you have a vector and its vector derivative, How do you position those two vectors? Yeah, they're orthogonal to each other. Awesome. So u of t is going to be like over here, and it's going to be like at a right angle or something. Or, sorry, u prime of t. Now, here's the cool thing. So you have your vector, and you have your tangent vector, which is orthogonal, and what happens when you cross them? What do you now get? Like, if you cross these two things, what are you going to get? Well, no, you don't get 0. They'd be 0 if you dotted them. What does the cross product give you? That's a good get. That's a good thinking, though. You're thinking of the wrong product. What does the cross product give you? The dot product would give you 0 if they were orthogonal. I'll give you a moment to think about it. Okay, think, look at your notes. Very close. You get another vector, but what is the relation of that vector to these two vectors? You're correct. It's orthogonal to both of them. So what you get is this other vector, which is the dot product, which is orthogonal to both. Okay, and this ends up being really interesting, and we'll talk about why really quickly. Let's say that here is your curve moving around. One of the vectors that you get is your u vector. Or so let's just say that this was the function u. So this would be your u vector. This would be your u prime vector. And now you get another vector, which is the cross product of them, which is orthogonal to both. So it forms a right angle with both of those. So this would be u cross u prime. So if you look at these three things, they form they're three axes. So they're sort of like an x and a y axis, or x, y, and z axis. Okay? So what this allows you to do is that it allows you to sort of like at any single point set up these axes where like your y-axis is tangent to the curve, your x-axis is determined by the curve, and then your z-axis is perpendicular to both of those. This actually has a special name, and it gets used in physics a lot. It's called a Frenet frame, named after the French dude who came up with this. So what happens is your u of t, your u prime of t, and u cross u prime form a set of three perpendicular axes. And we're going to talk about this. And if you're interested in studying more of this after this class, there's a math course called Differential Geometry when you go to a 4-year university. They just study all of this. It was like one of my favorite classes that I ever took. Okay, so let's actually do the calculation now. So like my whole point of like saying like why are we doing this as an example is because like it ends up being used a lot to do all sorts of shit. It ends up being used in like general relativity. Like has everyone heard of like Einstein's theory of relativity? We're all aware of this? Have we heard of this before? Yeah, so the math required to understand all of that is this differential geometry and vector calculus. And what it does is it allows you to like come up with a set of coordinates around you in space-time to express like the influence of gravity on the world around you.
two geometry concepts we already learned?
Sort of, yeah. You do geometry from the context of vector calculus, and this is like the basic intro to it.
Is there like a whole new list of, like, you know how we have the integral list or the derivative list? Is there a whole new list for that kind of stuff too?
You're thinking to basically, it takes all of that and uses it to explain geometry. So there's no new integral formulas. You use all that to explain like how you should think about geometry. Does that sort of make sense though?
Yeah.
Yeah, so it's not so much about calculating, it's like why does this shit work? Like how can you think of geometry in terms of calculus? Alright, so let's do this calculation. So the product rule tells you that you take the derivative of u. You have to cross it with u prime, and then you add to it u, which is then crossed with the derivative of u prime, which is going to be u double prime. So I think people were talking about this like the other day, like you were like, oh, would you ever have to take like the second derivative? Like here's an example where we're doing that. Alright. So let's go through and do the calculations. So let's set it up with component form. So what was our u of t here? Our u of t, just write it here so we can see it. Our u of t was t squared minus 3, 2t plus 4, comma, t cubed minus 3t. Okay, so if you take the derivative, you're going to get 2t, comma, 2, comma, 3t squared minus 3. And then you're going to cross that with u prime again, which is 2t, comma, 2, comma, 2t squared minus 3. And then you're going to add to that u, which is t squared minus 3, 2t plus 4, comma, t cubed minus 3t. Oh my god, is that a little kid? And then you're going to have to cross that. I thought I heard like a baby. With the second derivative of u. So when you look at u prime, you take the derivative again, you get 2, comma, 0, comma, 4t. Oh my god, it is a little kid. I'm gonna mute you because I hear them in the background. As much as I love them, I hear them. It's throwing me off. There we go. Okay. So now we have to go and do these calculations. Ugh. Okay. So remember, how does it work if you call this U1, U2, U3, and you call this V1, V2, V3. If you want to calculate the cross product, you get another vector, and it's going to be U2, V3 minus U3, V2. Alright, so remember, if you're calculating the first component, there's this symmetry. You use the second and third components, you subtract them. And then the second component is going to be U1, V3 minus U3, V1. Oh, well, the minus around it. And then the other one is going to be U1, V2 minus U2, V1. Okay, so we're going to have to calculate that. I'm just putting the formula here in case you've forgotten. So let's go and calculate that for the first two. Okay, so U2 is 2, V3 is 2t squared minus 3, and then you're going to get minus U3, which is 3t squared minus 3 times V2, which is 2, and then comma, minus U1, which is T2, V3, which is 2t squared minus 3, And then minus u3, which is 3t squared minus 3 times v1, which is 2t, comma. U1 is 2t, so you get 2t times v2. v2 is 2 minus u2, which is 2 times v1, which is 2t. Holy crap. This is so long. Okay, so all of this that came from calculating that cross product. Now I need to calculate this cross product. So plus. Okay, so let's do this. Let's name everything u1, u2, u3, v1, v2, v3. Okay, here we go. So u2 is 2t plus 4 times v3, which is 4t, minus u3, which is t cubed minus 3t, times v2, which is 0. Yay, that's going to make that one easier because this term will just go away. Okay, and then you're going to minus, okay, so formula says u1, which is t squared minus 3 times v3, which is 4t, minus u3, which is t cubed minus 3t, times v1, which is 2, comma, u1, which is t squared minus 3 times v2, which is 0, so that's going to go away, minus u2, which is 2t plus 4 times v1, which is 2. And that's going to go away because it's minus. Oh man. These are intense, yes? Like having just to go through and do all the calculations. Am I like the only one who feels that way? Okay, cool. I was like, maybe it's just because it's early in the morning, but I'm like, damn, this is just a lot. Yeah, and if you mess up on something small, it's like it falls apart. Okay, so let's calculate that first derivative. I'm sorry, the first cross product. So let's like multiply everything out and simplify. So like if you multiply this out, you're going to get 4t squared minus 6 minus 6t squared plus 6. So the minus and plus 6 will cancel. And you'll get 4 squared minus 6t squared, which will be minus 2t squared. Okay, what about when you multiply this out? You get 2t times 2t squared, which is going to be 4t cubed minus 6t minus 6t cubed plus 6t, and there's a minus around all of that. But notice once again that this minus 6t and that plus 6t are going to cancel. So you get 4t cubed minus 6t cubed, which will be minus 2t cubed. With the minus in front of it will give you positive 2t cubed. Okay, now you go to the next one. 2t times 2 is going to be 4t minus 4t. Okay, cool. So those cancel and you get 0. Nice. I like that. Okay, then you move on to the next one. Okay, so you multiply this through, you get 8t squared plus 8t. Now you go on to the next one. Sorry, like my brain just froze there for a moment.
Isn't it 16t?
Shit, thank you. Thank you. I can't do 4 times 4. That's me weeping. I'm so sad. Thank you for catching that. It makes me happy because at least I know you guys are paying attention. Sometimes I'm like, holy shit, I'm like the only one doing this. Okay, so we multiply through 4t cubed minus 12t minus 2t cubed plus 6t. The 4t cubed minus 2t cubed is 2t cubed. It would be minus 2t cubed. And then minus 12t plus 6t will be minus 6t, but then you have the minus on front, so positive 6t. Okay, then you go on to the next one, that's 0. You multiply that through and you get minus 4t minus 8. Okay. And then you add those two vectors together. So by components, so you take like the x components, you add them together, so it's going to be 6t squared plus 16t. Then you add these components together, the 2t cubed and the minus 2t cubed cancel, leaving you with 6t. And then the 0 plus that one will be minus 4t minus 8. Boom! There's your vector. Wow, that was like a lot of work. Whew! I like want to take like a break after doing that one. I'm just like, damn, like that was long. Jesus. That was like really long. I'm gonna pause. Okay. Whew. That was a lot. Okay, so we're gonna talk now. I already talked a little about why you'd want to do these calculations. I just want to know, should I wait longer? Are people done copying it? I just don't want to move forward. If people want...
A bit more?
Okay, cool. That's just what I want to know. I just want to know if I should wait, so I will wait.
Can you actually scroll up a bit? Thanks.
Hey, Professor, this is a random question, but what makes this different, like from the Wronskian solutions?
Wait, from the what? Makes it different from what?
Like the Wronskian?
Oh, shit! The Wronskian is related to this, because the Wronskian uses a determinant. So, and, like, this is very connected to the Wronskian, yes. They use a similar calculation.
Oh, okay, cool.
Isn't you...
I just mean like the correlation, it like looks the same almost.
Yeah, no, it should look similar. Wait, so someone's saying, isn't u prime crossed with u prime 0? If you cross something with itself, should you get 0? I'm thinking.
I think that's right.
Yeah, I did not get 0, did I? I got 0 for one of the components. Okay, let's look. Let's see if I made a mistake somewhere. Oh, shit. So I fucked up because I wrote it down wrong. No! Okay, I see the I made a mistake somewhere. These two things right here are u prime crossed with u prime, which means they should be the same. And they both have 2t, they both have 2, but look what did I fuck up? The third component, right? Ah, shit. Okay, we have to go back and change that, because I wrote it down wrong. It's supposed to be, they're both supposed to be 3t squared minus 3. Crap. Shit. I like apologize so much. I'm like so sorry. Like one little slip of my mind like screwed that up. Luckily it only changed some of it. So let's go through and fix that. Okay. U2 times V3. Oh, yeah, I messed that up right here. Because this is supposed to be 3t squared minus 3. So when you multiply that out, you get 6t squared minus 6. Oh yeah, and look what happens. The 6t squared and the minus 60 squared and the minus 6 and the positive 6, which gives me 0. Okay, and then same thing happens. Okay, so actually there's an easy fix to this. What do we know that all of this, whenever you cross it with itself, you're just supposed to get 0, 0. So I screwed up there. Because I copied the numbers over wrong. My bad. Oh, which means, actually this is not that hard to change then, assuming I didn't make any mistakes for the other one. Because this is just a bunch of zeros, what is my answer just going to end up being? That vector right there. So actually it's not that bad. Assuming that I didn't make any mistakes elsewhere. But let's go check. Did I screw up the other calculation? Because that's a good question. Damn. Sorry. Okay, did I screw up anything on the other one? Okay, my u is t squared minus 3, 2t plus 4, t cubed minus 3t. Okay, cool. I crossed that with the second derivative of u. Oh, no! I made a mistake because I looked at the wrong one. You take the derivative of 2t and you get 2. You take the derivative of 2 and you get 0, but I took the derivative of my messed up one. The derivative of 3t squared minus 3 is not 4t. Oh, crap. Does
that mean you have to start all over?
No, because we just need to change. I only made a mistake in that one component. So I just need to go and fix those. We do not need to start all over. Because, does that make sense? I only made a mistake in one part. So, like, I just have to go and change those parts. Okay, so we can salvage this. Okay. Let's just slowly go through and fix all of that. Okay, so we're going to start right here. We're going to get u2, which is 2t plus 4, times u3. So this is not 4t, it's supposed to be 6t. So whenever there's a 4t, I just need to go and change it to 6t. Okay, so there's two places where you have to change that. Okay, actually, this is not that bad. Okay, so that 4t got changed to 6t. You're going to get 12t squared plus 6 times 4 is 24. 24t. Okay, so let's go change this one. You're going to get 6t cubed minus 18t. Okay, cool. Okay, so this changes a little. Okay, so you get 12t squared plus 24t, comma, 6t cubed minus 2t cubed is 4t cubed. Minus 18 plus 6t is minus 12t. You have a minus around all of that. And then you get your minus 4t minus 8. Oh, cool. And that actually is the right answer, because I have the answer written down here, and this is it. Whew. Okay, what's the lesson to learn here? What is the lesson to learn about doing these calculations?
Be very careful.
Yeah. Because you screw up one thing and it, like, all that air propagates, right? So you have to be, like, super careful.
Check 10 times, do it only once.
Yeah. Yeah. Be careful. Is the lesson here. God damn. Oof. Whew. Okay, that was a little hard. Okay, now, the reason we're interested in this is because of that Frenet frame I was telling you about earlier. Okay, so, should I wait here longer? Or can I move away from here? Does anyone want me to wait here while more copying is done? I just don't want to move forward if people are still, like, copying over.
I think you can move forward.
Alright, cool. Okay, so there's something that we want to talk about, which is called the principal unit tangent vector. Okay, and I want to do this with an example. So let's say that your function r of t, your vector valued function, is given by cosine ti plus sine tj. So what does the graph of this look like? Like, if we graph this, what's the shape of this graph gonna be? What is the shape of this graph? If you graph cosine t is the x parameter and sine t is the y parameter. Do we remember? We talked about this when we did parametric equations a while ago. It is a circle that looks like this. It goes counterclockwise. Okay. Actually, let's just enter in. Let's just draw in a circle so it looks pretty. There we go. I always forget that I can just do this. Okay. Now, let's draw in a vector like right here. Okay, so you get this point in this vector by plugging in some t value, let's call it t naught, into there, right? So that's r of t naught. Okay, and we've been talking about this how if you plug t naught into the derivative, you get this, which is the tangent vector. Okay, so this will be r prime of t naught. Okay, and what do you know about the tangent vector and the original vector? They are what? What are they?
Orthogonal.
They're orthogonal, so they form a right angle. Okay. Now, so we call this right here is the tangent vector. But we're interested in something called the principal unit tangent vector, which we always write as an uppercase T. And this is defined to be the tangent vector divided by the magnitude of the tangent vector. Okay, and then this only works if the bottom is not equal to what? What can the bottom not be equal to? Because we're dividing. I should put the little arrow. 0. Okay, cool. Now, what is this operation that I'm doing on the bottom here? Like, the bottom is what? What are we doing to the vector r? It's like, what is this thing called? Where you have the two bars. Like, yeah, it's the magnitude. Good. Okay, so whenever you divide a vector by its magnitude, what you get is a vector with magnitude 1, which is why this is called the principal unit tangent vector. So what this does is it gives you a tangent vector, but the magnitude is always 1. And this ends up being useful because, like, let's say that you draw one of the vectors over here, and this is r of t1. Maybe at that point, the tangent vector that you would get is really long. So r prime of t1, maybe its magnitude is 5. And then maybe you draw a vector over here. This will be like r of t2. Maybe its tangent vector has a really small magnitude. Maybe its magnitude is half. So does it make sense that as you move around the curve, your tangent vector may have different magnitudes? Like at some places the magnitude may be very large, and at some places the magnitude may be very small. The principal unit tangent vector is nice because the magnitude always ends up being 1. So you don't have to worry about what the magnitude is. And for a variety of reasons, this ends up like being useful, basically. So does that sort of make sense? Like, we want a tangent vector that always has a magnitude of 1 for a variety of reasons. So we're going to end up using this later. For now, you just need to know that it exists. Okay. So anything we want to ask, I'm going to give you a moment to write it down. Okay. Can I go forward? It's sort of sad when I teach this. Like, does it make sense because I studied this a lot? I know that there's like this cool, beautiful theory about where all this goes, but like, you know how like when you learn math, you learn all these skills, like maybe in high school you learned like in algebra 2 how to factor and shit like that, and then like eventually it's like you're working on some calculus problem for a limit and you need to be able to factor to be able to get somebody to cancel to calculate the limit, and then you're like, oh shit, I see why like we learned about that in high school. Like whenever I teach this, it's sort of the same thing, because I can imagine that you're looking at this and you're like, what the hell, like why do we care about this? Like I get at it, like, you know, like it just looks like random stuff, but like there's this cool, beautiful theory that this ends up getting wrapped up in, like I was talking about the Frenet frames, and like part of me wishes that like we could just like sort of discuss that or learn about that, and it's like an odd thing. So I was just like reminiscing on that. I'm gonna move forward because I look at this and I'm like, oh man, there's so much cool shit to say about this, but then I don't want to just like drone on about it forever.
Like, you mean like we're on the cusp of learning something brand new and we can't talk about it right now just because we don't know?
Yeah, basically, yeah. It's like I need to tell you like 50 more things, and then we could talk about it. Do you get what I mean? It's like that sort of sucks because I like, for me, I'm like, oh man, there's all this cool stuff, and I'm like, oh, I need to wait because they need to like go through and like learn the rest of the chapter before it's really gonna make sense. And then like that means like there's like a bunch of random crap we have to go through first, like this stuff that's coming up now. So we talked about how to take the derivative of vector valued functions. Now what are we gonna have to do? So we talked about the derivatives of them. What else do you do in calculus?
Integrate.
Yeah, cool. Yes. So now the question is like, well, what does it mean if you're going to do the indefinite integral of some vector valued function? So let's say that r of t is a vector valued function. Let's say that's a plane curve. So you have the x component will be f of t, and the y component will be g of t. So in component form, you would write this as like f of t, g of t. Okay, so what does it mean to integrate this thing, or do an indefinite integral? Well, actually, let's move this down. There we go. Okay, so that's the same as integrating f of ti plus g of tj. And do you remember how in the limit of the vector valued function we split it up into limits of the components? It's the same thing here. So what you're going to get is the integral of f of t dt, and then what will all that be multiplied by? Your vector value, your vector unit vector I, and then you're going to get another integral of g of t dt multiplied by the unit vector j. So here what I'm doing is I'm integrating a vector valued function. So how do you integrate a vector value function? Well, you're going to split it up into two regular integrals. Here we're integrating a scalar function. But then what are you multiplying that integral of a scalar function by? This vector. So you have to realize that when you integrate a vector valued function, you end up getting another vector valued function, but you calculate that by splitting it up into these two individual ones. So when you integrate a vector valued function, you get a vector. Okay. And this works the same for when you do definite integrals. You're going to split it up into two definite integrals. You're going to go from a to b of f of t dt, and then you're going to multiply that by I plus the definite integral from a to b of g of t dt times j. Okay, and the same thing works. Let's say that your r of t, instead of a plane curve, was a space curve. So if your vector valued function had 3 components, what would your integral get split up into? Like, do you see how, like, in the first example, I had 2 components, or the I component and a j component, and you got 2 integrals with an I and a j? If you have a vector in space with 3 components, how many integrals are you going to end up with? 3, an integral for I, an integral for j, and an integral for k. Yeah. Okay. That was 3.2. I think we're just going to end here. I feel really hungry. My brain feels fried. I don't think I can do more. I'm going to leave this up for a moment. I'm going to wait to get responses. How's everyone today, though? Before we finish, let me stop the recording, then we can talk.